okay. I didn't want to erase the proposition actually, so I will rephrase it or put it on again. Okay, so what we did was we took points on a curve and then constructed another curve that some variation of those points were on, where we could be sure that there are at least capital N of them, where capital N is an arbitrarily large number. And what would be nice would be given N, find M at least 1, such that this curve, still the same curve, has at least N integral points with co-prime coordinates. So yeah, I erased it, but with our construction we multiplied all the denominators by the same factor, so they definitely have they are definitely not co-prime. So this would exclude our special construction, but this is not known in general. So our construction is the only answer how to find this. And it's even not very easy to compute or small to compute. So for n equal to 3, the smallest known m is this one. And this number of points here is always meant in a way that we don't count x, y, and yx. So this will count as 1 point, a point that is, so for example, this is 141. Otherwise, odd n would not make sense. So we would, of course, have also the points 76, 141, and this one, and this one. But in our way of counting, they count as 1. 1, 2, 3. So this is for n equal to 3. And what we could also do is we could require x and y to be positive. Then it gets, of course, even larger. And for n equal to 4, and x and y positive, no m is known. So in this case, with coprime coordinates. And there is also a theorem of Silverman that goes a bit in the direction of counting, but we will also not prove it. Such that we can bound a bit the number of possible solutions. So x, y on the curve, but also with integral coefficients and with coprime coordinates. And the number of those solutions, so this is exactly what we this n from here, this is then bounded by k, where this is a constant that doesn't depend on the curve, so it could be maybe 5, it's probably like 10 to the 10 to the 10 to the 10, but this is independent of the curve, and then in the exponent we have the rank. And so this also makes sense a bit, because if the rank is 0, then this is just a constant. And of course, if the rank grows, then we get much more possibilities for integer coefficients on points. Okay. So I thought the lecture would end here, but fortunately, I prepared a bit of the next lecture already. But this is also the same topic, so it fits. So what we did today was the easy case, where we have this cubic that factors, that we could also use for other cubics that factor. So of course, this x cubed plus y cubed is only one case, but we can only also find other cubics that factor, and this will also be in the exercises where you are also given the factorization already. So this is not too hard, but it's probably a lot of calculations. So what about, for example, this? It doesn't factor. We will see this in a moment, so this is not obvious. And we don't even know if it has infinitely many or finitely many solutions. We cannot say anything. Wait a moment. The next theorem. Okay, the next theorem is basically the same as before. From the Siegel theorem, a bit different. We have 3 non-zero integers, and we look at this curve. So this is a bit more general than this with the factorization, but a bit less general than Siegel's theorem, because Siegel's theorem was general for any cubic, and here we have this specific form. And we want to play around a bit now with this equation to rephrase it in a way that it fits into Diophantine approximation. And then next week we will talk about the heart of Diophantine approximation and maybe prove some things and maybe only talk about some other things. Okay, so what can we do? We can multiply this equation by a squared to get this. And if necessary, you'll see in a moment when it's necessary or not, we replace y by minus y, and maybe also b by minus b. And then we get the equation x squared minus x cubed minus by cubed is equal to c. bc integers, and both positive. So if b in the beginning was not positive, then we switch it. And to make this sign fitting, we might also change the sign here. And here we have the new x, which is the ax from before. Yeah. So we want to concentrate on this equation. And since we saw that before with this factorization that went very well, we try to factor this also. So what happens if we factor that? We need some number. We call it beta, which is just the cube root of b. And then we can factor this. So then this is just x minus beta y, x cubed plus beta xy plus beta squared y squared. And now we use the same trick as before, where we bounded the height of the solutions. So since x squared plus beta xy plus beta squared y squared is x plus 1 over 2 beta y and 3 over 4 beta squared y squared. Since we have this is a square, so it's positive. So this is at least 3 over 4 b squared y squared. And what else can we do? See on the right-hand side, well, we actually don't need the absolute value because we said it's positive. This is x cubed minus by cubed this is just the factorization that we had before. And now we just take the estimate from here. So this is at most, this stays the same, times 3 over 4 beta squared y squared. Okay, what does that tell us? We have C, which is a fixed number that we are given at the beginning because it just comes from the curve. And then it has two factors, this factor and this factor. So that tells us if this factor gets small, then this factor gets large, and the other way around. Now we divide by this thing. And then we get that x minus beta y is at most, put it on the other side, 4c over 3 beta squared y squared. Y squared. Oh, I have a y cube here, but that's... no, we also want to divide by y one more time. Divide by y and get x over y minus beta. It's at most 4c 3 beta squared times 1 over this. Yeah. We divide by the absolute value of y. Okay, yeah. What's this? So this here, beta is the cube root of b, which is not a natural number and also not a rational number, because otherwise we just could have factored this. So this is not a rational number. This is a rational number. And we want to approximate basically a not rational number by an irrational number by a rational number and have this bound here. And to say something about this, we have the Diophantine approximation theorem, which will then be the topic of the whole next lecture probably. Sure. So Diophantine approximation theorem. So the Diophantine approximation theorem tells us if we have a cube root here, actually it's also valid for other things here, but in our case, if we have the cube root of something that's not a perfect cube here, so it's irrational, and we want to find PQ such that P over Q is close to it, then we can only have finitely many of those solutions. So C is fixed, and depending on the on the size of the denominator, we can only find finitely many ways to approximate cube root of B in a good way. This has many nice consequences. I once had a lecture on this topic, and I think proving this theorem took like 3 lectures, and then we did things with this theorem for the next 5 lectures, and I loved this lecture. It was wonderful. So one could do a whole lecture on Diophantine approximation and would have no problem to find topics. But for us, it would show that here we only find finitely many x and y such that this holds. And we saw that this must hold if x and y is an integral point on our curve or on our equation ax cubed plus by cubed equal to c. So from this Diophantine approximation theorem, this follows immediately by this calculation. Now the question is how to prove this, and this is what we will do in the next lectures, and this is everything that I prepared, so I miscalculated again, and the lecture is finished today early. Thank you very much.